Hello. Good afternoon. We will start in a few minutes. We will wait for some time to if someone wants to add in the meeting. In this tutorial, we are studying the course Numerical Methods of Finite Difference Approach. The instructor for this course is Professor Amya Kumar Nayak, and he is affiliated to the Institute IIT Roorkee. And I am the TA for this course, so like I have to conduct some tutorials in order to clear the students' doubts with the respective course. My name is Vibhor Singh Yadav, and I am a PhD scholar at IIT Madras Department of Mathematics. So this is our fourth tutorial. In the previous tutorials, we have discussed about different finite difference schemes in order to solve the partial differential equations and why they are necessary and are more efficient. We use the finite difference schemes to solve them. What is the benefit we have discussed earlier. Then we have discussed some finite difference schemes in order to solve the parabolic partial differential equations, or the you can say heat equations. And the last tutorial we have discussed the different numerical schemes in order to solve the elliptic partial differential equations and second order heat equation. So in last lecture, we have seen that to solve a second order two-dimensional heat equation, one must use the ADI scheme, which is more efficient than those classical Crank-Nicolson and Schmidt schemes. As in those Crank-Nicolson scheme, we will get a pentadiagonal matrix, which will be difficult to solve. Whereas in ADI scheme, we will be having a tridiagonal system of matrices. So, and as we have already seen that in ADI methods, there will be two steps involved while solving for the n plus 1 at time level. So first I will go from n to n plus half, and then we move to n plus half to n plus 1. So that's what we have discussed up till now. So today we will proceed how to solve hyperbolic partial differential equations. So for that, first we will consider. So we are discussing hyperbolic PDs or hyperbolic partial differential equations. So first we will consider a wave equation, which is again a hyperbolic PD. So we consider a wave equation that is nothing but del 2u by del t square equals to c square del 2u by del x square. So it is a one-dimensional wave equation. Here c is some speed or constant, or we can say constant speed. And the associated initial and conditions and boundary conditions are as follows. So initial conditions are u x comma 0, fx, and another one we will suppose del u by del t equals to gx. And the boundary conditions are u 0 comma t, say f1t, and u in place of 0 we will say a, the starting point, and u b comma t, it is f of 2t, where t is greater than equals to 0. Since time can never be 0, so t is always greater than equals to 0. Here, one thing you can note that, like earlier, we were having only one initial conditions in case of parabolic partial differential equation or heat equation. But here we are having two initial conditions, like two initial condition and two boundary conditions. So as we have seen, the number of conditions associated with any system of equation, if it is equals to the order of the differential equation or order of the PD, then it is said to be an well imposed problem. So here you can see that we are having second order with respect to both time and space. So we are having two initial conditions with respect to time and two boundary conditions with respect to space. So this given wave equation is a well posed problem. Now we will see how to develop a finite difference scheme in order to solve this numerically. Analytically, this can also be solved, but in case of a more complex problem or some complex values, it should be preferred to be solved numerically. So we will construct a different scheme for this hyperbolic PD. Now, the first step is First, we will let the step sizes. Let h be the step size in the x direction, and let k be the step size in time direction, that is t. Now we will construct the finite difference scheme. So first step is, if we consider central difference approximation for both the time and space, that is the second order central difference scheme, then we will get, if we use second order central difference formula for uxx and utt, we will get. So first, I will write what is the formula. So as we have seen in our very first tutorial, say delta u x and u is a function of x and t. So numerically, it can be written as u is p comma q. So q is with time and p with respect to the space dimension x. The second order central difference formula is u p plus 1 q minus 2 u p q plus u p minus 1 q divided by delta x square. Or as we have taken the steps as h, then it can be h square. So using the central difference formula, the given wave equation will result into uij plus 1 minus 2 uij plus uij minus 1 divided by k square. And for space dimension, we will have u I plus 1 j minus u I j plus u I minus 1 j divided by h square. So here we will consider uh, take r equals to kc by h square. uh, kc by h, which will imply r square will be equals to k square c square divided by h square. So this is a required finite difference scheme using the second order central difference formula, and we will simplify it further. Then we will obtain uij plus 1 minus 2 uij plus uij minus 1 r square times ui plus 1j minus 2 uij plus ui minus 1j. Or we write the term at j plus 1 time level on the left hand side and taking all the other terms on the right hand side. I will get r square u 1 plus I plus 1 plus ui minus 1j plus 2 times 1 minus r square uij minus uij minus 1. So let us number this equation 1. So this is the required final finite difference scheme in order to solve a hyperbolic partial differential equation, hyperbolic partial differential equation in one dimension, or a one-dimensional wave equation. Here you can also note that this is an explicit scheme. Also, this is a three-level scheme or three-level formula. How are we saying that it is three level? Since you can see here j plus one level we have to find. So we also have jth level and we also have j minus one level. So there are three time steps involved in a particular step or in a single step. So it is a three-level formula. Like if we see in the grid form, so we are using, say this point is j minus 1, this is j, and this is j plus 1. So we are using three time steps at a single time in order to arrive at a final solution. You can also see the truncation error for the scheme 1. This will be an easier part. You can practice it by yourself. So what you have to do, you just simply have to take all the right hand side terms on the left hand side and expand these terms using the Taylor series expansion and cancel out the common terms. Then you will be arriving at some terms that will remain that won't be cancelled. So we took out the first term from those terms, and the respective coefficients of that term will be representing the truncation error for this scheme. So I will write the truncation error. You can practice it out by yourself. So the truncation error, say TE, is given by k squared by 12, k del for u by del t4 minus h square del for u del t4 xi and t are the nodal points. And as we have already discussed in our earlier lectures, that the order of the method or order of the scheme is given by 1 by k times of the truncation error. So the order of the method is, or we will just divide it. So it will be order of method 1 is 1 by k times of that of the truncation error, and that is k square by 12 del 4u del t4 minus h square by 12 del 4u by del x4. So the sign doesn't matter, and the constant values that are the numerical values don't affect the order of the method. So the order of the method is k square plus h square. That is second order in time and second order in space, both. Next, also that we can see we have our two initial conditions. So what we can get out from those initial conditions. So initial condition is this one, u x comma 0 fx and del u by del t x comma 0 equals to gx. So this one is simply gives us u I comma 0 equals to f of xi, and this one gives. So here we will use the central difference formula. So So this is like a derivative initial condition. As we have seen the derivative boundary condition, similarly now we have a derivative initial condition. So using a central difference formula, we will be having u ij plus 1 minus u ij minus 1 divided by twice of k equals to g of xi. So you can also say the order for this term will be of order of k square, as we are using a central difference formula. And in central difference formula, we have the order of that difference formula is the second order. So we can directly say from that theory, the order of this term will be of 2 with respect to the time direction. So this can be solved further. So this will help us in order to solve the given difference scheme for hyperbolic partial differential equation in place where we do not have any information about the given nodal point. So from here we will have u ij plus 1 equals to 2 times of k g of xi plus u I j minus 1. So this is the scheme that we have. We will name it as number 2. So when will it be beneficial? Like suppose you have to fix j equals to 0. Then what will it give? It will be j ui comma 1 2k gxi plus ui comma minus 1. So whenever we are solving this different scheme 1 in place when we fix j equals to 0, then we do not have the negative time step. Since we do not have any negative time step, we have considered t is always greater than equals to 0. So in that case, in order to obtain that value, we will be using the derivative initial condition. So from here, you can obtain u I minus 1 will be equals to u I1 twice of k gi, where gi is nothing but g of xi. So this will be the benefit of this initial condition, that in case of negative time step, we can simply find the values using the scheme or the scheme 2. As I have said, now let us put j equals to 0 in 1. So what we will get is uh, u I1 equals to r square u I plus 1 0 plus u I minus 1 comma 0 is to 1 minus r square times ui comma 0 minus ui comma minus 1. So this will be in equation number 3. So as I have said, this term cannot be found from the grid or from the mesh, as we do not have any negative time step. So this can be substituted using the equation number 2. Also, from the initial condition, we are having ux comma 0 equals to f of x, or ui comma 0 equals to fi. Let us say we have assumed this notation. So this is another initial condition. Now we will substitute this one in the scheme in the difference equation 3. We will get ui comma 1 equals to r square fi plus 1 minus fi minus 1 plus twice of 1 minus r square fi minus ui, what we have here is that ui comma 1 minus twice of k gi, or we simplify it further. Here we have done nothing there, but just we have substituted the finite difference scheme obtained from the initial conditions for the given problem. So it will further just simplify our finite difference scheme to solve the hyperbolic PD. So further simplifying it, we will get 2 times of ui1 r square fi plus 1 minus fi1 minus 1 plus 2 times 1 minus r square by 2 times k gi, or simplifying it furthermore, it can be also simplified to ui comma 1 r square by 2 fi plus 1 minus fi minus 1 plus 1 minus r square fi plus k times gi. So this is our required finite difference scheme. So you can just simply given any problem a different f and g. Those are nothing, just the functions of x. You can just simply substitute them in this equation number 4, and one will be ready to find the numerical solution for a given hyperbolic partial differential equation. Also, we can have some special cases from this equation number 4. So say when r equals to 1, so if r equals to 1, then in this term it will become 0, it will vanish, and we will only be left with ui j plus 1, ui plus 1 j plus ui minus 1 j minus ui j minus 1. So this is what we can get from the equation 1, the very initial difference scheme that we have just constructed. And from this reduced difference scheme number 4, we will get ui comma 1, 1 by 2 fi plus 1 minus fi minus 1 plus k times gi. So these are this one is a special case whenever we have r equals to 1, so it will be simplified more further, and we will be left only with the three terms that we need to calculate and evaluate by substituting their values. So also one can note that it is much more similar to the second order wave equation, analytical solution of the wave equation, that is nothing but uxt equals to 1 by 2 times f of x plus ct plus f of x minus ct plus 1 by 2c integrate n x minus ct to x plus ct g of some function xi. So this is an analytical solution of a wave equation that is nothing but del 2u by del t square equals to del 2u by del x square. So this is the analytical solution. It is the kind of similar to that of the numerical solution, the outline of the solutions. Now we will see some numerical problems based on this different scheme. So let us question that find the solution on the initial boundary value problem. That is UTT equals to UXX, and the domain is given from 0 to 1, subject, and this wave equation subject to the following initial condition. Subject to the initial conditions ux comma 0 sin pi x and utx comma 0 0. So both in the domain is fixed, that is from 0 to 1. So this is nothing but del u by del t. It is just a different notation for that. And the given boundary conditions are u 0 comma t 0 and u 1 comma t is also 0. Time is greater than 0. So here, so in this question, we have to use explicit scheme, that is the scheme number 1 or 4, either one we can use. And we have to assume that the step size h is 1 by 4, r is given to be 3 by 4, and we have to integrate using the following explicit scheme up to 3 time steps. So this is the given problem, complete problem. So here we have a wave equation, that is UTT equals to UXX. The co-value of the speed, the coefficient C is given to be 1. And the following are the given initial conditions and the boundary conditions. So now we will see the solution for this particular problem. Here one can note that from the given problem that as C is given to be 1, step size is given to be 1 by 4, and the constant R is given to be 3 by 4. But we do not have any information about the step size in time direction. But since we know that R is nothing but Kc by H, so it will imply K will be nothing but RH by C, and we have all these values, so it will be 3 by 4 times 1 by 4, so it is 3 by 16. So the step size in the time direction is 3 by 16, and we have to integrate up to 3 time steps, so it will be like 3 by 16, start from 0, 3 by 16, and 3 by 16. And also we are given the, or the x dimension, the range is from 0 to 1, and step size is 1 by 4. So we will be having 1 by 4, 1 by 2, 3 by 4. Total number of nodal points will be next direction will be 0, 1, 2, 3, and 4. So total 5 points in next direction, and up to 3 times step we are finding. So 4 points in the time direction. Now we will proceed with the solution. Now we will use first, as we have seen while constructing the numerical scheme for the hyperbolic PD, we had used the initial conditions using the central difference formula in them in order to simplify our actual finite difference scheme. So we will use the initial condition So what is the initial condition? It is del E over del T equals to 0. Now, using a central difference formula, we will have ui j plus 1 minus ui j minus 1 twice of k is equals to 0. So here we will get ui j plus 1 equals to 2 times of k will be 3 by 8 ui j minus sorry, it will become 0 by multiplying to that side. So we will be left with uij plus 1 equals to uij minus 1. And here if we take j equals to 0, then we have ui1 equals to ui minus 1. So this is the term that we require, the relation that we need. And it is for all I 0, 1, 2, 3, 4. For all i's, this relation holds. Now we will write the explicit three time level formula. So the explicit three level formula is given by, as we have seen earlier, it is ui j plus 1 equals to r square ui plus 1 j plus ui minus 1 j plus twice of 1 minus r square ui j minus ui j minus 1. So this is the actual finite difference scheme. And also we have the value of r, that is nothing but e by 4. So 1 will imply ui j plus 1 will be equals to 9 by 16 ui plus 1 j ui minus 1 j plus 7 by 8 times uij minus ui j minus 1. Let us number this equation number 2. Now the next step, as we have seen, that we will put j equals to 0 so that we can find the values at the first time step. So put j equals to 0 into, then we will have ui1 9 by 16 times ui plus 1 0 plus ui minus 1 0 plus 7 by 8 ui 0 minus ui minus 1. So for this term, we will use the initial condition based on this relation. Therefore, we are using ui1 equals to ui minus 1. So this equation will imply ui1 will be equals to 9 by 16 ui plus 1 0 plus ui minus 1 0 plus 7 by 8 times ui 0 minus ui 1. So now we do not have to evaluate any negative time step, as we neither can do that. So rearranging these terms, one will arrive at this final scheme, that is ui1 will be 9 by 32 times ui plus 1 0 plus ui minus 1 0 plus 7 by 16 times ui comma 0. So let us mark this with star. So this is the difference scheme that we require to solve the given problem. Now our next step is we will change the values for I. That is I is running from 0 to 4. So first we will put I equals to 1 as at 0 we already know the values from the boundary conditions that at I equals to 0 and I equals to 4 the values are 0. So first I will take I equals to 1 in star. So it will give u1 comma 1 9 by 32 times u2 comma 0 minus u0 comma 0 plus 7 by 16 times u1 comma 0. Now from the given initial conditions and boundary conditions we have the values of these nodal points. So this will be 9 by 32 times 1 plus 0 plus 7 by 16 times 1 by root 2, and it will be equals to 0.59061. So here we have simply used the given initial conditions that ux0 is sine pi x and this all. Like we are having ux comma 0 equals to sine pi x. This is nothing but ui comma 0 sine pi h by 4, or this one. So when you need to find that u1 comma 0, then what will it be? It will be sine pi by 4, and it is nothing but 1 by root 2. And when you need the value of u2 comma 0, it will be sine 2 pi by 4. It is nothing but sine pi by 2, and it is 1. So here these are the values that we have obtained using the initial condition given. Now the next step, so this is the one value that we have obtained, that at u1 comma 1 will be 0.59061. You can cross verify this solution by solving it by yourself. And next step, you take I equals to 2 in star. So it will give u2 comma 1 9 by 32 u3 comma 0 plus u1 comma 0 plus 7 by 16 u2 comma 0. Now again we can have these values from the given initial condition. So 1 0 we have seen it is 1 by root 2, 3 0. So u3 comma 0 is nothing but sine 3 pi by 4. So it is nothing but just 1 by root 2. So here also we have 1 by root 2 plus 7 by 16 times u to 0. It is u nothing but 1. So after solving this one, the final value for u2 comma 1 is 0.83525. Next, we will take I equals to 3 in star, and it will give u3 comma 1 9 by 32 times u4 comma 0 plus u2 comma 0 plus 7 by 16 u3 comma 0. Again, we will use the initial conditions that are u4 comma 0 will be nothing but sine 4 pi by 4, that is sine pi, and it is 0. So this will be 0 plus 1 plus 7 by 16 plus 1 by root 2. So it is 9 by 32 plus 7 by 16 root 2. And the answer is 0.59061. So this is the required answer at the first time level for the third nodal point in x direction. So these are all the required values. Like we are having this grid. Here I equals to 0, 1, 2, 3, 4, and j is equals to 0, 1, 2, 3 that we have to find at 3 time steps. So we already know these values, that is t equals to 0, and these boundary points, we already know the values. So till now in this question, we have find the values for these points that are denoted by cross. Now we have to proceed in a similar way in order to find the solution at the second time level, those are, which are these, and particularly we will find the solution for these points. So for the next step, we will just put j equals to 1 in order to find the solution at the second time level in 2. Then we will get ui comma 2 equals to 9 by 16, ui plus 1 1 plus ui minus 1 1 plus 7 by 8 ui 1 minus ui 0. So this is the scheme they have just denoted by double star. Now again we have to follow the same way, that take I equals to 1, 2, and 3. Then we will get, like here as earlier, you are supposed to take I equals to 1. Then the scheme double star will form a more shorter version. Then you will just substitute their values and find a particular point, that is u1 comma 2, u1 comma 3, and 3 comma 2. Subsequently, you find all the values. So I will just write the answers. You can check it with your calculations. So the answers will obtain as u1 comma 2 will be 0.27951. u2 comma 2 will be 0.39528, and u3 comma 2 is 0.27951. So these are the values that we will obtain at the second time level. In similar fashion, put j equals to 2 again in equation number 2 in order to find the solution at third time level. So the resulting scheme will be ui comma 3 equals to 9 by 16 times ui plus 1 2 plus ui minus 1 2 plus 7 by 8 times ui comma 2 minus ui comma 1. It is denoted with by triple star. So this is the scheme that we need in order to find the solution at the third time level. Then again, you have to take I equals to 1, 2, 3 as earlier, and you will reach to a solution at the third time level that are denoted by, or those are, so 1 comma 3 value is given by minus 0.12369. u2 comma 3 comes out to be minus 0.17 493, and u3 comma 3 comes out to be minus 0.12369. So these are the solutions at the third time step. In similar fashion, you can proceed up to different levels, different time levels. You just have to iterate with the subsequent nodal point values, that fixing j equals to something that is the required time level, and then changing the values of I, whichever you need. So in this way, you can simply find the solution for the numerical solution for the hyperbolic TD or a wave equation. Now we will see one more question on the same concept. So the question says solve by explicit second order finite difference method UTT equals to UXX for two time steps. U0 given initial conditions are U0 comma T and U1 comma T, and also the del U by del T initial and boundary conditions is 0. So here the domain is from x equals to 0 to x equals to 1. And this is the given initial and the boundary conditions. And the another initial condition is ux comma 0 equals to 100 times x, 1 minus x. Also the step size is given to be 1 by 4, and the time step given to be also 1 by 4. So this is the question that we have to solve using again the same, this is the same hyperbolic partial differential equation that we have to solve numerically. So again, we will first note down all the information that we can get from the question itself. So here we are having, since R is Kc by H, so R will be 1 by 4 times 1 by 4, it will be 1. Value of R is 1. Also from the initial condition, that is ux comma 0, 100x, 1 minus x, we will have ui comma 0 equals to 100 times xi 1 minus xi. And this is a numerical representation for one of the initial condition. And we also have the del u by del t equals to gi, and gi is 0 here. So we have ui comma 1 equals to 1 by 2 f I plus 1 plus f I minus 1. Also, so these are just the information that we can easily obtain from the given question. Now we will write the finite difference scheme or the three-level formula, explicit formula for solving the hyperbolic partial differential equation, that is ui j plus 1 equals to ui minus 1 j plus ui plus 1 j minus ui j minus 1. That is number equation number 1. And from this initial condition, we will have like simply applying the second order central difference, the first order central difference formula, we will be having uij plus 1 minus uij minus 1 divided by 2k is to 0. This will imply ui1 equals to ui minus 1. So this is the relation that we obtain for all I 0, 1, 2, 3, 4. We can just simply use this relation in the given three-level explicit formula. Now, if we try to see the grid that we are required to solve, means that we have the x and t direction is represented by this. So the starting point is x equals to 0. Your step size is 1 by 4. So it is 1 by 4, 1 by 2, 3 by 4, and 1. And these are the time levels that we are required to find. So numerous time levels we can find, as we, in this case we are required only to find out two time steps. So like up to here we have to find. And from the given boundary conditions, that is u0 comma t equals to 0 and u1 comma t is again 0. That is nothing but u0 comma j is 0 and u4 comma j is 0. So from this, what we have is we can simply obtain the values on these points. Like these points are just the boundary points. So at these points, it is all u is always going to be 0. From these boundary condition. So at these point, u is always be 0. And the remaining terms, that is, we have ux comma 0, that is 100x, 1 minus x. So this is our initial condition. So using this initial condition with the respective problem, we can simply find the values at t equals to 0. So since u is a 0 here, but at this point, that is at t equals to 0, we can find the values of u on these nodal points using this given initial condition. That is that when xi is 1 by 4, you will get u equals to 75 by 4 at half. You will get u equals to 25 at this. You will get u equals to 4. And again, it is 0 here. But you can simply see ui comma 0 is 100 xi, 1 minus xi. So say u1 comma 0 will be 100 times 1, 1 minus 1 by 4. That is the step size at that point. So it will be 25 times 3 by 4. That is nothing but 75 by 4. In similar way, you can find all the values at the 0 time step along the x direction. So from these, like what we already have, we can write it first here, then it will be simpler to solve further. So say we have u value of u0 comma 0 as 0, u1 comma 0 as 75 by 4, u2 comma 0 as 25, u3 comma 0 is again 75 by 4, and u4 comma 0 is 0. That is again a boundary point. And we also have information about u0 comma 1, u0 comma 2, u0 comma 3, u0 comma 4, u4 comma 1, u4 comma 2, u4 comma 3, and u4 comma 4. These all are zeros. Since these are just the boundary points, and from the boundary condition we have at boundary u is 0, and also at the time step 0, we can, when the nodal point is 0 and 4, all the values of u at those points will be 0. So these values we already know at a first hand, and we will just use these values and try to find the unknown values. Now, for j equals to 0, or putting j equals to 0 in 1, we get ui1, ui minus 1, 0, plus ui plus 1, comma 0, minus ui minus 1 is ui1, ui minus 1, comma 0, plus ui plus 1, comma 0. Let us say number 2. You can note that here we have used the relation, that is ui1 is nothing but equals to ui minus 1. So we have a hybrid equation, or the scheme number 2. Now, as we have done in the previous question, we will change the values of I. So first, for I equals to 1, into we get u1 comma 1, 1 by 2, u1 comma 0, it is u0 comma 0 plus u2 comma 0. So it will be 1 by 2 times of 0 plus 25, which is nothing but 12.5. Next, we will put I equals to 2 in 2, and we will get u2 comma 1 as 1 by 2, u1 comma 0 plus u3 comma 0, which is again can be found using the values that we already have. That is u1 0 is nothing but 75 by 4, and u3 comma 0 is again 75 by 4. So final answer is 75 by 4. You can either leave the solution here or can proceed for the decimal values. Next, we will have I equals to 3 into, then we will get u3 comma 1, 1 by 2 times u2 comma 0 plus u4 comma 0 equals to 1 by 2 times 25 plus 0, again 25 by 2, or 12.5. So this is what we have up to the first time level. Now in similar way, we will proceed with the second time level. Now we put j equals to 1 in equation number 1, and we obtain ui comma 2, ui minus 1 comma 1, ui plus 1 comma 1, minus ui comma 0. So let us denote with the equation number 3. So in this step, we will obtain all the values at the second time step, as we have fixed j equals to 1, and on the left hand side we will have ui comma 2 that represents the solution of u at the time step 2. by using all the initial time steps, that is t equals to 1 and t equals to 0, that we already know from our previous solution. So here again, we will take I equals to 1. So it will be u1 comma 2, u0 comma 1 plus u2 comma 1 minus u1 comma 0. It will be 0 plus 75 by 4 minus 75 by 4, which is nothing but 0 itself. For I equals to 2, we have u2 comma 2, u1 comma 1 is u2 comma 1 minus u2 comma 0. It will be 25 by 2 plus 25 by 2 minus 25, that is again 0. Or we can directly say, like in this grid, you can simply see like along x equals to half, we have the symmetry that on both the side, that is on the right hand side and the left hand side, we are obtaining same value, that u equals to 75 by 4 and u equals to 75 by 4 on the either sides of x equals to half. So due to symmetry, we can also simply speak about the solution that we need. So here we will write directly, due to the symmetry, one can say directly about the solution at u3 comma 0 and u3 comma 2 and u1 comma 2, that they will also be, and or either can be obtained as 0 only. So these are the required solution at time step 2. Now we will proceed for j equals to 2, that is fixing j equals to 2 in 1. Then we will get the scheme as ui comma 3 equals to ui minus 1 comma 2 plus ui plus 1 comma 2 minus ui 1. Here we will having the third time step solution on the left hand side, which are obtained by using the time step solutions at time level 1 and 2. Let us number this as equation number 4. So simply we have to again follow the same procedure, that is put I equals to 1 in 4, then we will get ui u1 comma 3 equals to u0 comma 2 plus u2 comma 2 minus u1 comma 1, which is nothing but minus 25 by 2. And for I equals to 2, we will have u2 comma 3 equals to u1 comma 2 plus u3 comma 2 minus u2 comma 1. So in this case, the answer comes out to be minus 75 by 4. And again, due to symmetry, as we have seen here, that like let us say this is the point of symmetry. So this point and this point will always, and these points are always going to be have a same values. Like with this, the value of this will be same, and this, and for this, the value is gonna be same. So again, for the third time step also, using this concept of symmetry, we can answer about the other nodal points as they would be minus 25 by 2. So one can directly answer the solutions at these points using the concept of symmetry with these. Don't have to evaluate at each point. You just have to notice whether the given problem is following the symmetry or not. If it is following the symmetry for one time level, you can check whether it is symmetric or not. it is symmetric, then you don't have to evaluate for all the points. The efforts will be half. Like if you need at 5 points, 4 points, then you will only need to evaluate at only 2 points. The other 2 points can be answered using the previous points only. Let us take one more question on the same concept. So here what the question says is evaluate the pivotal values for the equation del 2u by del t square 25 times del 2u by del x square, where the domain of x is from 0 to 5 and t is greater than 0. And the given initial and boundary conditions are uh, boundary conditions are at x equals to 0, we will have the value of u is 0, and at x equals to 5, again the value is 0. And the initial conditions are one is utx comma 0 will be 0, and the another initial condition is ux comma 0 is equals to 20x when x is from 0 to 1, and 25 times 1 minus x by 5 when x is 1 to 5. So this is the given initial conditions and the respective boundary conditions for the given problem. Also, it is given that the step size is 1 in x direction and in time direction is 0.2. So this is the problem that we have to solve. Uh, First, we will note down what we have. We have the value of c square equals to 25, which implies c is 5, h is given to be 1, k is given to be 0.2, which implies r is going to be kc by h, that is 1 by 1 equals to 1. So r is also 1. Also, we have certain boundary condition, that is u 0 comma t will be equals to u 0 comma j 0 for all j 1, 2, and so on. And the another boundary condition says u5 comma t, that is u5 comma j is 0, again for all j 1, 2, 3, and so on. And the initial condition data, we will have del u by del t at x comma 0 is uij plus 1 minus uij minus 1 divided by 2k at xi comma 0. So it is nothing but it is ui minus 1 equals to ui comma 1 for all I equals to 0, 1, 2, 3 to 5. So with these points, so this is the required relation that we have obtained for the negative time level. Uh, Using these boundary conditions, we have the following information also, that is the following points we already know the values, that u 1 comma 0 it is 20. U 2 comma 0 is 15. U 3 comma 0 is 10. U 4 comma 0 is 5. And U 5 comma 0 is 0. So this is initial data that we have from the boundary conditions and the initial condition using this initial condition, that is u of x equals to 0 of x comma 0 is 20x and 25 times 1 minus x by 5, respectively for the different respective domains. Now, as we have r equals to 1, the explicit three-level formula is uij plus 1 equals to ui minus 1j plus ui plus 1j minus ui j minus 1. Since ui1 is nothing but ui I minus 1, using this relation in the above equation, say 1, then 1 will imply and take j equals to 0, then we will get from 1 that ui1 is to ui minus 1 0 plus ui plus 1 0 minus ui minus 1, which is nothing but ui1 equals to ui minus 1 0 I plus 1 0 minus ui1. And simplifying it further, we will obtain ui1 is nothing but 1 by 2 times ui minus 1 0 plus ui plus 1 comma 0. So this is the required finite difference scheme to solve the given problem. Let us number it 2. Now again, as we have done earlier, we will change the values of I and try to find out the solutions at the respective nodal points. So take I equals to 1. We will have u1 comma 1 equals to 1 by 2 times u0 comma 0 plus u2 comma 0 is 1 by 2 times 0 plus, and u2 comma 0 we already have 15, so will be 15 by, so u2 comma 0 is 15 by 2. Similarly, for I equals to 2, we will have u2 comma 1, 1 by 2, 1 comma 0 plus u3 comma 0. So it will be 1 by 2 times, here we have I 1 comma 0 is 20 and 3 comma 0 is 10. So it will be 10 plus 20, it will be 15. Next, for I equals to 3, u3 comma 1 is equals to 1 by 2 times u2 comma 0 plus u4 comma 0. Again, we can note the values from here that u2 comma 0 is 15 and u4 comma 0 is 5. So it is 20, therefore it is 10. Similarly, for I equals to 4, we have u4 comma 1, 1 by 2, u3 comma 0 plus u5 comma 0. Its value will be 1 by 2 times 10 plus 0, as this is the boundary point. So it's using the boundary conditions, value is 0. So the required answer is 5. So these are the solutions for the first time step with the different nodal points at I from 1 to I from 0 to 5. Next, we will fix j equals to 1 in equation 1, and we will get ui comma 2, ui minus 1 comma 1, ui plus 1 comma 1 minus ui comma 0. And again, we will just keep on changing these values. So it will be for I equals to 1, we have u1 comma 2 equals to u0 comma 1 plus u2 comma 1 minus u1 comma 0. 0 plus 15 minus 20, it will be minus 5. And again, if we do it for I equals to 2, then it is u2 comma 2, 1 comma 1 plus u3 comma 1 minus u2 comma 0. So the values for this is 15 by 2, u11 is 15 by 2 plus 10 minus 15, so it will be 5 by 2. Similarly, for I equals to 3, we will have u3 comma 2, u2 comma 1 plus u4 comma 1 minus u3 comma 0. So it will be 15 plus 5, and the value of u3 comma 0 is 10. So minus 10, the answer comes out to be 10. Also, one more point we need, that is I equals to 4. So for this, we will have u4 comma 2 equals to u3 comma 1 plus u5 comma 1 minus u4 comma 0. So for this nodal point, we will have 3 comma 1 is 10, 5 comma 1 is 0, and u4 comma 0 is 5. So the required answer is 5. So these are the required points that we have obtained. These are the solutions to two time level or two second time step using the explicit difference scheme. One can proceed in the similar way to obtain the values for higher order terms. So this is what we have discussed about solving the hyperbolic partial differential equations using the finite difference approach. Next, we will discuss some other problems based on the SOR method and the Gauss-Seidel methods. So in this, we will discuss some assignment problems. So some problems based on SOR method or the Gauss-Seidel method. Uh, Let me see the problem. So the problem is if the Poisson equation, so Poisson equation is nothing, just the Laplace equation or elliptic partial differential equation. So with the Poisson equation, that is del 2u by del x square plus del 2u by del y square equals to f of x y is solved by SOR, that is succession over relaxation method, for Gauss-Seidel method, then which of the following is true? Uh, Given options are, or you can just see this question in your assignment. I will just directly solve the solution, get to the solution part instead of writing all the options. You will think that it will take too much time to write these options. So this is the question, that if a Poisson equation, one second, that if a Poisson equation, that is a Laplace equation, is solved by SOR for Gauss-Seidel method, then which of the following is true? So here, what we are doing is, I will let you know what we are doing in this question. We are generating a numerical finite difference scheme for this respective question. So the given Poisson equation is del 2u by del x square plus del 2u by del y square equals to f of xy. So we will use second order central difference formula for both these terms. That is second order central difference formula for all these terms. Then the resulting numerical scheme will be appear as that ui plus 1 for x, it will be ui plus 1j minus 2uij plus ui minus 1j divided by delta x square, and delta x is the step size in the x direction, plus ui j plus 1 minus 2uij plus ui j minus 1 divided by delta y square. It is equals to f of xi y I, or you can say yj. So this is the required difference scheme. Here we suppose that both the step sizes in the both directions are equals to h, that delta x is to delta y, and that is denoted with h. Therefore, the scheme will be uij equals to 1 by 4 times ui plus 1j plus ui minus 1j plus ui j minus 1 plus ui j plus 1 minus h square fi. So this is the simplified version of the above difference scheme. Now what we have to do, like we have to use the SOR method for the Gauss-Seidel method. So in Gauss-Seidel method, I will just recall that what is the Gauss-Seidel method. In Gauss-Seidel method, we are trying to solve the system of equations, that is x, or let us say some matrix of coefficients this and xn, and this can also involve n plus 1 term also. So at a different steps, like n plus 1, we will keep on changing the values of n and try to find out the solution using the Gauss-Seidel method. This is what the Gauss-Seidel method you might have studied in the basic numerical analysis course. So we will keep on changing the or keep on updating the values at the different steps subsequently, so that we can arrive at the final solution. At one point of time, we will having the same values, like for say n equals to 20, in 21 we will have the same values of the unknowns of x, the unknown x. Then there will be that will be a stopping point, and we will stop at that point. So this is what the Gauss-Seidel method is. One more method is that Gauss-Jacobi method, which is most kindly the same, but it is much slower than this one. At that method, we will not update different step values subsequently in the system, but we do it at different time steps or different levels, you can say. Not basically time steps or different levels, you can say it might be time or space, anything. So we have to use the SOR method for those siders. So it will be, and also since SOR method is, let's say some x to the power k plus 1. A k plus 1 is not a power, it is a level that is we are representing. 1 minus omega x to the power k plus omega x to the power k plus 1. So this value we have to obtain from the Gauss-Seidel method. Write it. This value from Gauss-Seidel. That is nothing, as I have already shown, that x k plus 1 can be defined u I j plus 1. So these are the values that we will obtain using the Gauss-Seidel method. Using this concept, we will see that our equation, let us say equation number 1, it will be modified to that uij n plus 1 equals to 1 by 4 times ui plus 1 comma j n plus ui j plus 1 and ui minus 1. Here we will take n plus 1 at level for these terms, n plus 1 minus x squared fi this. What we have done, we have used this concept of SOR method. That's what we have taken the explicit for these first two terms and implicit for the next two terms. So it will reduce to uij n plus 1 will be equals to 1 minus omega uij n plus omega by 4. It will be ui plus 1 j n plus ui j plus 1 plus ui minus 1 j plus u j minus 1 n plus 1 minus h squared times function f ij. So this is the required scheme, and it is one of the correct option that we have. It can be cross-checked using the given options, and it is one of the options that we have for the above question. Next, we will see one more problem. So the problem says that which of the following is the Poisson? Again, we have the same Poisson equation, that is del to u by del x square plus del to u by del y square equals to f x y. And we have, if solved using SOR for Gauss-Seidel method, given that the maximum number of given that the maximum number of grid points along x and y direction are both very large and given by m and n respectively, so the grid points are denoted by m and n respectively in the x and y direction. So you have to select which one of the following options is correct. So the options are, option A is top 2 minus root 2 cos pi by m square plus cos pi by n square whole to the power half. Option B is omega equals to 2 minus root 2 pi 1 by m square plus 1 by n square to the power half. Option C is omega opt equals to 2 minus root 2 pi 1 by m plus 1 by n to the power half. And option D is omega opt will be equals to 2 minus root 2 pi. Times 1 by m square plus 1 by n square to the power half. So in this question, you have to choose which one of the following options is the correct one when we use the SOR method or the Gauss-Seidel method, given that the maximum number of grid points along x and y direction are both very large and represented by capital M and capital N. So we will try each and every option and see which one is wrong and which one of them can be the correct one. So we will start option 1, that is 2 minus root 2 times sine pi by m square plus sine pi by n square whole to the power half. So in this method, we know that for small x, we know for small value of x, we will have that sine x is approximately equals to x only for any small theta or small x. Also, since m and n are very large, as it is given in the question, therefore pi by m square and pi by n square will be very small, which will imply using the above property that sine pi by m square is nothing but approximately equals to pi by m square, and sine pi by n square is approximately equals to pi by n square. Therefore, let us number these equations as 1 and 2. Now combining both these equations, one can simply arrive at that omega will be equals to 2 minus root 2 times pi by m square plus pi by n square whole to the power half, and it will be equals to 2 minus root 2 pi 1 by m square plus 1 by n square whole to the power half. We will take the pi common outside, then it will be root pi. Then one can simply note that option B is the correct one, because we have obtained this by solving the given problem. Therefore, option B is the correct answer for the above problem. You can simply check for other options also, and you will come to know that other options will be incorrect with the given problem. So the option B is the correct one as we have solved here. We will take one more problem on the SOR and Gauss seidel. So now we will see one question on the stability analysis. So the question is, if we have del u by del t equals to del 2u by del x square plus del u by del x, and if we try to solve this PDE using the von Neumann stability analysis, by using forward difference for the temporal derivative, also given in the question is that we have to use forward difference for temporal derivative and central difference for the spatial derivative. Then which of the following solutions will be the correct one? So this is the given question that we have to solve this given partial differential equations using one like first we have to develop a difference P using forward difference for the temporal derivative and the central difference for the spatial derivative. Then we have to check using the von Neumann stability analysis whether the scheme is stable, unconditionally stable, or unstable. So for that purpose, first we will see like from von Neumann stability analysis we have the solution will be of form u p comma q xi to the power q multiplied by e to the power theta ph. So this is the form of the solution that we require that we will substitute in this given problem. So first we will construct the finite difference scheme. So for that, we'll substitute the forward difference. Substitute the forward difference for the temporal derivative, that is u p comma q plus 1 minus u p q divided by delta t, and central difference scheme for the spatial derivatives. So first we'll use the second order central difference, that is u p q minus 2 u p q plus u p minus 1 q divided by delta x square plus u p plus 1 comma q minus u p minus 1 comma q divided by 2i's of delta x. So this is the first order central difference formula, and earlier I have used the second order central difference formula for the second derivative. So the required scheme. Simplifying further, we will have u pq plus 1 minus u pq is equals to r u p plus 1 comma q minus 2r u p comma q plus r u p minus 1 comma q plus s u p plus 1 comma q minus s u p minus 1 comma q. Here r is delta t by delta x square and s is delta t by twice of delta x. So we have used the respective notations. So simplifying it furthermore, we will get u p q plus 1 will be equals to r plus s u p plus 1 comma q plus 1 minus 2r u p comma q plus r minus s u p minus 1 comma q. So let us denote by equation 1. Now we will substitute the solution of form UPQ equals to xi to the power q e to the power iota beta ph in 1. That is what the von Neumann stability analysis says. So substituting this from 1 can get e to the power iota beta ph xi to the power q plus 1 equals to r plus s e to the power iota beta p plus 1 h xi to the power q plus 1 minus 2r e to the power iota beta ph xi to the power q plus r minus s e to the power iota beta e minus 1h xi to the power q. Then we will take some terms, repeating terms common from the right hand side for the simplification purpose. Therefore, we get xi to the power q e to the power beta ph, and it is r plus s e to the power beta h plus 1 minus 2r plus r minus s e to the power minus iota beta h. Now cancelling out the common terms from both the sides, we will get the value for xi, that is xi is r plus s multiplied by cos beta h plus iota sin beta h plus 1 minus 2r plus r minus s cos beta h minus iota sin beta h. So these are just the representations, the trigonometric representations of sine. That is, we know that cos theta is nothing but a to the power iota theta plus e to the power minus iota theta minus 2, and for sine theta it is e to the power iota theta minus e to the power minus iota theta divided by 2 iota. So we have just used these results to simplify our equation. Then we will have xi equals to r times cos beta h plus, we'll simplify and open up the brackets. We will get iota r sine beta h plus s cos beta h plus iota s times sine beta h plus 1 minus 2r plus r cos beta h minus iota r sine beta h s cos beta h plus iota times s sine beta h. So from here, one can simply note that these terms are common, so this can be cancelled out. Now, after cancelling out these terms, our given expression will reduce to psi equals to 2r cos beta h minus 2r plus 1 plus 2 times iota sine iota s times sine beta h, and simplifying further, it will be xi will comes out to be 2r 1 minus 2 sine square beta h by 2 plus minus 2r plus 1 plus 2 iota s sine beta h. Here we have converted the from cos to, we have changed from cos to sine. But we have used the formula of cos to theta, that is nothing but 1 minus 2 sine square theta. So using this formula, we will arrive at this term that we have converted into the sine function. Now, sending 1 to the other side, it will be minus 4r sine square beta h by 2 plus 2 times iota s. If 2r minus 2r will be cancelled out, it will be left, we will be left with sine beta h, which is nothing but xi will be equals to, if we take modulus on both the sides, it will be 1 minus 4r sine square beta h by 2 to the whole square plus 4s square sine square beta h whole under root. So this is the correct option. That is the required condition for the above difference scheme to be like for to be the stable one, like unconditionally stable. Here what we have done is like if we have z equals to x plus iota y, then modulus of z is nothing but x square plus y square whole under root. So we have used this concept here in order to obtain the following relation for the amplification factor xi. Here xi is the amplification factor, as we have discussed earlier also. As the stability of any difference scheme depends on this xi, whether if it is greater than 1, then the corresponding scheme is said to be unstable. And whenever it is less than equals to 1, the scheme is said to be stable. So now I will wind it up with this lecture. In this tutorial, we have discussed different. First, we have discussed the to solve the hyperbolic PDE using the numerical the finite difference approach. Then we have discussed few problems based on that concept of by solving different types of by solving hyperbolic PDEs with different types of initial and boundary conditions. Later, we have discussed some problems based on the SOR method for Gauss-Seidel, and then we have discussed one stability problem based on some given partial differential equation. So in this question, we have constructed the different scheme for the problem start, and then we use von Neumann stability analysis in order to find the stability condition for the given problem, and the stability condition is given by this modulus of xi. So this is all up for this tutorial. Thank you.